So welcome all of you to the QFE. It's a great pleasure to have you join us today. We're doing this virtually, and the reason is that we are very fortunate to have with us today Lars Hansen from the University of Chicago, who is one of the great thinkers and economists of our generation. And as you probably all know, he's a recipient of Nobel Prize in 2013. And he's going to talk about uncertainty, quantification, decision theory, and the economics of climate change, which kind of digs deeply into how we make decisions and how we deal with uncertainty when it's of a very fundamental kind. And I'm looking forward to hearing about this. He'll talk for about 50 minutes, and then we'll have 10 minutes of Q&A at the end. So Lars, the floor is yours.
Sure, thank you. I appreciate this opportunity to share some thoughts I have, and certainly we'll be welcoming feedback that you might have. I'm going to be talking across a few papers here. This is the basic idea here is we want to be thinking about uncertainty in broader terms than is typically taught in economics classes, where lots of focus is on so-called risk, and what happens when we broaden those considerations, and then how should we think about that if we want to make prudent decisions. And then I'll be reserving the last chunk of this talk to talk about an application of climate change, which I've been spending a substantial amount of my research efforts on in the last couple of years. So this is just some recent papers that we have related to today's talk. I won't delve into the details of it of each of them. I'll be covering issues across these though. So this starts off with, I had this statistician's wisdom. Whenever you write down models in economics, formal so-called structural models of economics, they're wrong. We think they're useful, we think they're valuable, we think they're insightful, but there's always a danger in pushing them then beyond where they're most appropriate to use. And so here I've quoted, boxes. I could quote many people on this. Boxes pointing this out, that really models we use are approximations or simplifications, and if they weren't that, they wouldn't be very useful anyway. That they'd be far too complex, and there's no really easy way to describe a complex reality fully. So this is the box quote is it'd be very remarkable if we happen to write down simple models of things that captured everything. There's another theme that's going to carry through here. They'll become a little bit more evident as I develop the ideas further. And this goes back to one of the initiators of so-called robust Bayesian methods, Irving Good. Now, Irving Good actually wrote a book called Good Thinking. I guess it's a very clever title, of course, but given the author. Actually, I don't think that book is the best book in the world, but it's got a great title. But Good is kind of whenever people use some variant of things called min-max or max-min type theory, which will be an aspect of to what I'm talking about, when can this make sense? And he then wants to say, well, maybe you should go back and look at really what you're guarding against, these least favorable distributions, and see how reasonable they are. And that's, I'll be certainly reporting calculations that have this spirit in them as well. Now here's the thing that kind of keeps me up at night in some sense. Whenever we talk about scientific evidence and we want to influence policy, there's this concern that if we acknowledge the limits to how much we know, the policy makers or public won't take us very seriously. And then there's this exaggeration or this tendency to want to sweep the uncertainty under the rug or not really explore it openly. And so this is a quote by Hayek in his Nobel address, that even if true scientists should recognize the limits of studying human behavior, as long as we have a public, there's be people who will pretend or believe they could do more to meet popular demand than what is really in their power. It's kind of a warning that if we don't put this uncertainty up front and central, if we have a pretense of too much knowledge, we could possibly be led astray. And I think this is something important to think about, and what I hope is developing more sensible quantitative methods for incorporating uncertainty makes uncertainty something that we can push to the forefront and not kind of bury behind the scenes. So the statistical theories, there's a kind they're typically taught in statistics and even econometrics classes that go back to Wald, Savage, and there's a very kind of elegant treatment of it in Ferguson's book as well. The axiomatic treatment goes back to Jimmy Savage. There's under which there's the axiomatic approach to subjective probabilities, also building on the ideas of DiFinetti and others, under which there's subjectivity is recognized as something important, but then we treat it probabilistically. There's then other strands of this that try to avoid the subjective prior inputs altogether, leading to things like partial orderings, admissibility. And there's the so-called complete class theorem that kind of connects these two, trying to say that admissible decision rule can often be supported by Bayesian priors. Now, the type of decision theory that interests me is one that goes kind of beyond this notion of purely subjective probability, and recognizing that subjective inputs are important, but that we may have uncertainty about what those subjective inputs should be, and this opens the door to formalizing things like ambiguity aversion as distinct from risk aversion. So roughly speaking, think about risk aversion as a situation where we know probabilities but not outcomes, and this ambiguity aversion is when we don't necessarily know probabilities with full confidence. We have some ambiguity about what those assignments should be. And there's different variants of this. There's the one axiomatized by Gilboa and Schmeidler, which is closest to robust Bayesian methods in their usual form, max-min expected utility. There's a smooth ambiguity aversion of this. There's variational preferences, and then there's this interesting distinction between subjective and objective rationality in a paper by Gilboa, Mascheroni, Marinacci, and Schmeidler. So these are the various different literatures out there. Now, I'm going to be kind of building on pieces of each of these literatures in ways that I'll try to make clear, and also extending them in ways that I think are important. Now, what's happened in the decision theory coming out of economics is it's shifted its orientation much more to revealed preference theory, and created a little bit of a distance between statistical constructs. And so most of it is, and so these ideas of likelihoods and priors, which are central objects in statistics, are often obscured in this economics literature. And so we want to bring those back, back to the forefront in ways that are useful. So the findings are we're going to have a kind of a modification of Savage-style axiomatic formulations. I'm not going to get into the details of the axioms today. Just let you know that they're very that they exist and are out there. We're going to be distinguishing concerns about likelihood functions that might be misspecified and priors, which we may not know with full confidence. And when I think about these as two different concerns, there's kind of potential misspecification of a likelihood and potential misspecification of prior. Now, one can easily imagine ways to connect these two, and I'm going to actually develop some ways to try to distinguish them that will become more clear. And when I think about model misspecification, it's kind of the former, and then robust Bayesian methods are meant to kind of confront the latter. So we want to integrate both likelihood and prior uncertainty into formal treatment of uncertainty quantification. Now, let me be, this term likelihood gets often used and abused in different ways, and in some sense, I'm going to be abusing the term here. The decision theory I'm going to really be talking about at the outset is going to be static, and these so-called likelihood functions are nothing more than parameterized distributions over uncertain outcomes. So a lot of the decision theory uses the so-called Anscombe-Allman framework, where one defines preferences over so-called acts. And in the Anscombe-Allman framework, an act is maps a state into a probability over outcomes. Right? So, so we're going to use in a static setup, we're going to use this in a very special way. We're going to think of a state as a potential parameter value that indexes a particular model. Each model is going to induce a probability distribution over outcomes. So associated with that state is going to be this probability distribution, and Nance going to element it's some lottery. And so that model is going to have predictions about random stuff. Our models may be able to have shocks. So shocks have distributions, and once I know those distributions, then I get these probabilistic predictions. So a model is going to, once I commit to a model, I can basically be back in the risk type framework where I know probabilities but don't know outcomes. Okay, now it should be really clear here. By model, we can be models for different things. For model, I'm going all the way to condition on unknown parameter values. So I think of each model, a model as also a full specification of the underlying parameter value, and then I may be uncertain about what that parameter value is, or I may be uncertain about which model is correct. Okay. And then a probability distribution over states, since the state is a parameter value here, is just a prior distribution. Okay, so this issue about how we assign priors over these parameters, and there's issues about whether these probabilistic specifications might be flawed. So in the static, to represent this stuff in a static setup, I'll comment subsequently about the dynamic extensions that are very important. We want to consider a parameterized model of some random vector with a realization W. Think of W as some like shock that's going to occur in the future, and then I'm given this potential distribution over these shocks, and that's given by this density L of W given theta against some common measure d tau. And then and so for these to generate probabilities, then I want to be able to, the integral over the W's then to be equal to 1 for every choice of theta. Now within this setup, I'm perfectly happy with theta being infinite dimensional, so we can talk about we can open the door to non-parametric Bayesian methods and the like. It doesn't have to be finite dimensional. Now I'm going to introduce a construct. Which I'm going to call a prize rule. And what this rule is going to do is if I pre-specify a gamma, it's going to depict an uncertain outcome, or so-called prize, and it's going to element language of a decision. So I might make an investment decision today. It's going to have a random outcome, and what gamma tells me is how that outcome depends on tomorrow's shock, and then so typically these gammas are going to be restricted to a set of functions indexed by a decision. This is what's given in the last slide here. This gamma of W might be some big gamma of a D in W, where D is in some type of action space. And so these gammas are, we used to call them decision rules, but they're not decision rules in the sense of Markov decision theory, because these are things that are going to just be these mappings that tell us if I knew W, I would know what the uncertain outcome was. And so, and then the issue is how I put distributions over W. So then subjective expected utility, I'll savage as you come up with a prior, I'll just call it pi naught. I'm going to represent preferences by taking a utility function, U, evaluated at gamma of W, that integrate L. And so this is preferences, and then I'm going to integrate over theta. So basically, subjective utility theory has us treat in a very symmetric way the probabilities conditioned on models, as well as the probabilities over these different parameter values. The latter being the subjective, and the former being the specification of a model. So this is just standard expected utility theory. Now we want to break this a little bit. We want to break it up in a little bit and generalize it. So I need to look at things. I need to perturb some stuff here. I need to look at modifications of things. So I'm going to have these set of likelihoods and priors. So for each theta, think of this M of W given theta as just a way that I can shift the likelihood a little bit. And I'm going to restrict this little m to be in a space big M. And the restriction is just going to tell me that if I integrate this little m against L d tau, I get 1. And all that's telling me is that this M is like a is essentially a likelihood ratio relative to L. And so it's just going to give me a new probability distribution over the W's for each choice of theta. Okay. So it's just going to be a way for I start jiggling things around or move away from my initial specification of the likelihood. Now I also want to jiggle around priors, and so for that I'm going to take some baseline prior, say d pi naught, and I'm going to jiggle that by just by multiplying by, again, this kind of relative density, if you like, n of theta, or density against the baseline prior, and that has to integrate to 1. So as I'm going to introduce, I'm going to look at m's and n's. And the 1 is going to be, the m's are going to give me the form of the model misspecification. The n's are going to give me the way to look for prior sensitivity. Okay, oops, wrong way. So I'm also going to use statistical divergences. I find this a valuable construct. There's huge families of statistical divergences. I'm going to stick to the family called phi divergences, and I'm going to introduce 2 of them, a phi m and a phi p. And these are divergence between probability measures, and they're constructed by a convex function such that phi of 1 is 0. I'm just going to normalize it so the second derivative at 1 is 1. And then what I'm going to be doing is I'm going to form a statistical divergence. Is I'm going to take phi sub little m. I can evaluate that at some m and integrate out. And by Jensen's inequality, that has to be bigger than or equal to 0, because I know that m has to have an integral of, has to integrate up to 1. So, and I know that phi of 1 is equal to 0. So that gives me something that's always bigger than or equal to 0. It'll be equal to 0 if m is identically equal to 1. Okay. So I can form one of these for the m's, and I can do I can also form one for the n's. Okay. Now, in our calculations, one of these divergences that's really very, very simple and tractable, and it has been used a lot in applied math literature, is the so-called relative entropy or Kublak-Leibler version of it. And there I'm looking at the log likelihood ratio, basically, and I'm going to integrate it with respect to the alternative M model or N prior, depending on which application. And that has a lot of very nice properties. Where in this static setup, we can proceed more generally, but in a lot of our applications, we end up using this type of divergence. It's got nice links to statistical discrimination as well. Okay, so prior divergence. So here, as I indicated, I've got this baseline prior. I'm going to consider alternative priors of this form. I just introduce an n. And then I can form some alternative prior. Okay. Now this n here, I should have restricted. At this point in time, I'm going to restrict. This slide is a little bit messed up here. The n should be some n naught as a function, as a subset of n. Think of it as some convex subset. I may not want to look over every possible prior, and I'm going to represent preferences over gamma in this fashion. It's going to be the, I'm going to be minimizing the expected utility here. There's no potential misspecification of L. It's just in the end. So I'm just looking at the distribution, changing probabilities over parameters. And then I'm going to put on this divergence term because I'm going to penalize movements away from some baseline. So somehow the baseline is the starting point, and I'm going to penalize movements away from it. And then the preferences, I'm going to, for every gamma, I'm going to rank preferences by solving this minimization problem. And so this is where so-called min-max comes into play, because typically you'll then maximize this objective by choice of decisions. So now let me talk about these comments about prior divergence. We're going to, with this formulation, we can actually reinterpret previous contributions to decision theory literature as representing prior ambiguity instead of model misspecification. So it's a paper by by Strzelecki and Econometrica that claims to be about misspecification. Well, this formulation is actually about a prior misspecification, not model misspecification. Now, also with relative entropy divergence, the implied preference orders agrees with this substantial literature called smooth ambiguity preferences, but it's rationalized in a completely fundamentally different way. That literature never makes references to prior uncertainty or prior ambiguity here, but that interpretation we find valuable, and so we kind of prefer this link to the whole smooth ambiguity literature. So the entry point into one of these kind of relaxations of Savage decision theory is just through this prior ambiguity. Now, how about potential model misspecification? Okay. Now, suppose we condition on a specific theta. I'm going to kind of repeat the same type of steps. I'm going to replace this L with something multiplied by M, so I'm going to allow it to be perturbed. Then I'm going to rank these alternative gammas conditioned on theta by solving this minimization problem. Okay. So now I'm going to be minimizing this over M, but this is all conditioned on theta. So we end up doing this. You can do this theta by theta, and then again I need a penalization parameter, the C sub M. So these penalization parameters, C sub M or C sub P, get very, very large. That's just going to push you back into standard expected utility type calculations. And as we make it more modest, as we penalize, as we reduce the penalization, that's increasing the amount of robustness or reducing the cost of robustness. Okay, so this part of the literature links to what's called robust control theory, typically in that literature, there's no discussion of parameter uncertainty. It's just about models are potentially wrong. So so we get at that by conditioning on a specific theta. But of course, we want both, and we want to put both on the table here. I'm sorry, this is basically repeats what I just did. Let me go to the next one. So what I want here is I want both. Again, I'm going to let this N0 be a convex subset of N. I'm going to represent preferences over gamma with the following. Remember that when I did the misspecification over M, that was theta by theta. So now what I'm going to do is I'm going to take that, I'm going to average that criterion with this altered prior, N of theta, d pi of theta. Okay. Then I'm going to do the same thing for the divergence penalization, which was theta by theta. I'm going to integrate that against d pi of theta. Then what I'm going to do is I'm going to minimize that over the set M. So basically what I'm going to be doing is putting a set of priors on the table, and I'm going to be investing misspecification theta by theta over this entire set of priors. And then I'm going to be minimizing over that set of priors. Okay. So I'm both minimizing the potential model misspecification subject to penalization, but I'm also minimizing over the set of possible priors. Then in this case, the contribution to a divergence is 0 whenever this M is equal to 1 for some N. So if you can hit the models you care about without the misspecified likelihood, then in fact this contribution will be 0. But then but we want to allow for more forms of misspecification than just I'm just coming from priors here. Okay. So there's another variant of this, and this will be the one that I'm actually using in some calculations. Instead of constraining the set of priors, I'm going to do this divergence penalization instead. And this now gives me two penalization parameters, C sub M and C sub P. One is this kind of likelihood misspecification, and the other is the prior misspecification. And this then gives me a joint divergence over M and N. Okay. So this is a way that we kind of handle these two different types of misspecifications with this type of form. Now, notice, we can get into to some mathematical subtleties here. If one can say, why not be like non-parametric Bayesian? So if I go non-parametric Bayesian, there's mathematical results that say that you necessarily have to concentrate prior probability over a meager set. That's just a result from probability theory. And if we're going to impose absolute continuity of our priors with respect to a baseline prior, we're going to be spending all of our time in that meager set. When it comes to doing model misspecification, we no longer have that restriction to that so-called meager set. So the sense in which we're looking over something much, much bigger than we could capture with a prior probability distribution, even if that is over a so-called infinite dimensional set, parameter space. So we want to use this now to get at this idea of extending uncertainty quantification. Now, what do I mean by this? So I want to entertain prior and likelihood uncertainty. I've shown you two ways to do it, subject to penalization. Now, we're always doing this kind of minimization, okay? And then the decision problem is you go maximize after you've, so you first do the minimization choice by choice, and then you maximize over the choices. Now, for a lot of these problems, the min-max theorem applies, and I can just reverse orders. What that means is that I'm always optimal against some particular specification of a probability distribution over W's given thetas and some prior over thetas, these so-called worst case likelihoods and priors. Then we can go look at those and see what they look like and see whether they look crazy or not. The concern about min-max theory is that, well, maybe you're guarding against something that's really stupid. And this has to do with how we set these penalization parameters guard whether we're looking over whether we're allowing a huge amount of robustness or kind of very little robustness. And so they also then, those same penalization parameters determine what decision theorists would call an ambiguity aversion or aversion to a model misspecification. They're determined by these penalization parameters, which I mentioned on these statistical divergences. So it's not our job to tell a policymaker how averse they should be to uncertainty. So the best we can do is do sensitivity analyses over these as they change these penalization parameters. So as I change these penalization parameters, what's going to happen is I'm going to get different courses of action and different probabilities over over these worst case, computed by these worst case calculations. The models of which are optimal against. And so this is a type of sensitivity analysis which we find to be revealing. And the uncertainties that we're feeding into this could be very, very high dimensional, but at the end of the day, this collapses it down to a two-dimensional set. And it's picking out the forms of misspecification that really ought to be most impactful to the decision maker. Maybe these are the places in which you might want to close knowledge gaps. Maybe these are the places where you might want to search for more expertise or the like. But they help you isolate kind of what parts of these inputs really matter for the decision problem at hand. So there's dynamic counterparts to all this. Here's some references that address them. We basically use recursive methods that build on in some of these same type of ideas using dynamic programming type formulations. So the dynamics, we use conditional counterparts to previous analysis. When we're exploring the consequences of misspecification, now we're misspecifying Markov transition dynamics. We can use martingale theory to kind of help do that in very useful ways. Again, we want to explore the consequences of priors / posteriors. Now, why do we put priors / posteriors? Well, in a dynamic setup, I always like to think of today's posterior is tomorrow's prior. So, I mean, so we want to do robustness analysis over those entities. It turns out that dynamic consistency issues show up. I'm not going to have time today to elaborate on those, but there's ways to confront them. But there is an interesting tension that shows up vis-a-vis dynamic consistency, which we and others have discussed in the literature. So a formulae for the dynamic problem amounts to as this. If we're in continuous time, we're going to solve a two-player zero-sum differential game. It's a stochastic differential equations for state evolution. We're going to, in the problem I'm solving, there's both diffusive as well as kind of jump components to this. One player is the fictitious player, say say, maximizing social well-being or maximizing its own private well-being. The other player investigates the adverse consequences of uncertainty to these about the probabilistic inputs, either concerns about misspecification of the model or of the prior. We typically use relative entropy to limit or bound the probabilistic uncertainty, although one could use other divergences. And then numerical PDE methods with extra twists in the computations. So basically we end up solving this max min dynamic problem with two outputs. We're going to get this altered probability specification that isolates the uncertainty components that are really most consequential, but we're also going to get a decision rule then that performs well, hopefully, over a wide range of probabilistic specifications that potentially are of interest to us. And so that's kind of how the formalism goes in dynamic setup. I don't have time to set up that notation because I really want to talk about an application of this stuff, be more concrete. So now let me turn the rest of my time, the remaining 20 minutes or so, to climate policy under uncertainty. There's many calls for immediate climate policy implementation. There certainly are limits to our current understanding about the timing and magnitude of climate change and its impacts. And this has led to the apprehension of some. Some will use this as an excuse not to act. We say, well, since we don't know stuff, we should just wait until we know stuff. But there's nothing about decision theory that tells you that you need to wait, because the decision theory under uncertainty says that the possibility of bad outcomes may be enough to make you want to act now, because it may be much less costly to act now than to wait in the future, when once you know things, you may have already done some irreversible damage to the economy or the environment. So we're going to discuss, study out a stylized decision problem in which the decision maker is going to confront uncertainty, in which is going to be this future information about how severe the damages are. We're uncertain now about the damages, but at some point in time, we're going to get a lot more certain. Once we start damaging the environment, it's going to be all the more evident that these damages might be severe, or maybe they're more modest. But at some point in time, we're going to find out. But the value of the future empiricism in the near term is going to be limited. So rather than writing down all the equations, the model absent climate change is going to be a simple so-called AK model. We can add on expiration for reserves, so there'll be a capital stock from which there's output can be an investment or produce intermediate goods. Also, resources from that output could be used in expiration to produce new reserves. Those reserves, from those reserves, then we draw down emissions. Intermediate goods and emissions combined into some final consumption good, and that then determines economic well-being. So far, no climate concerns. So now let me add those in here, the so-called climate externality here. At the same time this emissions is combining into the final consumption good, it's also altering the climate. As it alters the climate, then that damages the economic opportunities. And this is the part, is the so-called externality, and this is the place where the invisible hand kind of breaks down, and there's scope for tax policy, cap and trade policies, or various different interventions. Now, there's another source of uncertainty that's important that we're in the process of fully integrating into this, and that has to do with, we might use some of the investment to engage in research and development. This research and development may in the future deliver some form of clean energy. There's uncertainty as to the timing and the magnitude of that improvement, and but then that of course can influence economic well-being in a positive way, because it can limit the amount of kind of dirty technologies or maybe dominate dirty technologies in the future. So these are the type of model ingredients which we have. Now let me just lift out the type of uncertainty components that we're going to be inputting into our calculations. So what I did here is went to the climate science literature, and we got out predictions of so-called pulse experiments. So these pulse experiments say, take your model of the climate system and put in a pulse over a year that amounts to 100 gigatons of carbon, and then and then report what happens. Okay? And the different models have different predictions of what happens. This is a way that climate science sometimes will do model predictions or model comparisons, sorry. So in this setup, in our calculations, we're going to have 144 different models, but these models are going to be combinations of two things. Some of these models are focusing on the mapping from emissions into carbon in the atmosphere, and some of it's more focusing instead on the mapping of carbon in the atmosphere to temperature changes. And so we have model combinations going on here when we construct these 144 different combinations. So what I plotted here is the outputs of these 144 different model simulations from these pulse experiments. And the blue dashed line tells you what the average response is, averaged over all the models. And then also the red line gives you the 75th percentile, the green line, the 25th percentile, and then I also give you the upper and lower envelopes. Now, right now, these are just model tabulations. I could convert these into probabilities if I wanted, if I assigned every model ex ante equal probability. So if I weighted them all the same, then I can turn these percentiles into probabilities. Now, the important thing to us is the fact that there's this pattern that all the models agree that there's a kind of a peak effect at about 10 years, and then things flatten out. And what matters to us is the decade-long increase is not so important to our calculation. It's kind of where it settles down. That's important. And there we see rather wide divergence across these predictions. So it's rather substantial uncertainty about what the responses will be, and this is one source of uncertainty that interests us. Okay. Now we can't input 144 different climate models into our economic model. That's impossible, and so we're going to put in simplified dynamics to try to capture figures like this instead. So now I'm going to just kind of pose a stochastic model of damages, and it's. If you look at the literature, the economics literature, a lot of this damage functions are proportional reductions in output or consumption due to climate change, and so we're going to follow that type of calculation. But we're going to put uncertainty as to what the damages are. Different people have asserted different amounts of damages. There's the range of damages that have been used in calculations is really quite substantial, and so we're going to have uncertainty about damage curvature captured by this kind of shaded region here. I'm going to actually put a whole bunch of different damage curves here. So think of these curves as telling you proportional reductions in say output and capital. And so beyond the temperature threshold of 1.5, then there's that's where the divergence starts. So as I indicated before, we're going to have this experiment where at 1.5, what happens is the damage curvature might become more severe, but we're going to give the decision maker the knowledge of it once you cross the threshold. So this is almost like a tipping point in the sense that if you cross 1.5, then all of a sudden, there's big damages, potentially big damages down the road, or they end up being possibly modest. Now, there's been discussions. It used to be people would talk about 2-degree thresholds, anomaly thresholds, now 1.5. I guess currently we're about 1.1 or so. So we put in that uncertainty as well. And so it may be that the jump takes place, that this revelation takes place at degree 2, anomaly 2, and then beyond that, the damages become much more severe, and there's that, and then the curvature takes place. So for us, the way we're going to think about this as a single Poisson event, there's going to be this Poisson event that kind of that's with an intensity that depends on the temperature anomaly, and that a temperature anomaly that intensity is going to get all the more likely large as we get closer to 2. It's going to be essentially 0 until I get to 1.5. Then it's going to kick in, and so there's going to be a probabilistic jump somewhere between 1.5 and 2. Then once I jump, I'm going to be on one of these different damage curves, and so at the jump point, you're going to know what curve you are. Before that time, you don't know what curve you are. And then for the purpose of this calculation, the climate uncertainty is not going to get resolved. So as Poisson event is kind of for us, it's kind of this metaphor for future information is going to occur which we're going to find out a lot more about climate change. Okay, so as I talked about, when we solve this problem, we can allow for ambiguity. So the ambiguity could be over those weights of those alternative climate models. I said we could start off equally weighting them. But then that equal weighting is kind of arbitrary. What happens if we allow a little bit of a shift in that away from equally weighting all 144? And so that's a type of ambiguity aversion or not, or this prior uncertainty. And so what happens in our calculations is the red histogram just captures that limit point of those pulse experiments. And the blue histogram shows you the tilting that takes place coming out of our decision problem. And you're going to tilt a little. You're going to tilt towards the right. Why? Because it's the high climate sensitivity, which you really fear. And so a cautious move is going to have you do a probabilistic shift towards the right. And that's what's captured by this figure. This is for a particular then penalization parameter. Now, the other form of uncertainty has to do with this jump process, and under which there's this Poisson jump, and then there's this uncertainty about where you jump to. We're going to think of that as a form of model misspecification, potential model misspecification. We can write down some baseline Poisson jump model, in which we have a bunch of curves, say 20 different curves that we make equally likely, and we have this kind of Poisson specification. This for the jump itself, but those could be wrong. Yeah. So as I indicated, we have this jump process where the temperature is temperature dependent. It's going to be more likely as the temperature anomaly increases. It's going to be a single jump, and then once you jump, there's this the damage curvature is revealed. So the jump distribution then assigns probabilities to each of the possible damage curvature parameters prior to the jump taking place. And then after that, it's realized. Misspecification shifts both of these things. And I'm going to be showing you what it's doing to the weighting of the alternative model of the curvatures here, but actually shifts both. And so here I'm showing you a type of sensitivity analysis, 3 different penalization parameters. The gamma, think of the gamma 3 here is just the curvature in the damage function. So 0 continues a baseline, and then as I move further on, things get more and more curved. The red histogram treats them all equally likely. Okay, and that's just a flat region going across. And then a little bit of model misspecification concern shifts that distribution a little bit to the right. And that's given by the blue curve. Now, if I want to activate more concerns about model misspecification, that shift gets all the more substantial, and that's given by the middle curve, and the curve all the way, and sorry, the middle density, and then the density all the way to the right, then is a much more severe concern about model misspecification. So, arguably, we could say the middle one is a more moderate form of model misspecification, and it's potentially interesting. Maybe the one on the right looks too severe. Now, of course, if I make that penalization parameter smaller and smaller, I'm just going to tilt things more and more toward, I'm just going to load everything up towards the upper end point. And so it becomes degenerate. So it's an intermediate range that really interests us here. And so this is a type of sensitivity analysis which we do. Now, I'm not, here's the social cost of carbons that come out as a function of the temperature anomaly. Remember the anomaly, we're about 1.1 now, and the anomaly triggers a jump sometime after 1.5. So I'm just plotting things up to 1.50. And I'm doing this on a log scale. And so the baseline says, I don't care about this uncertainty. I'm just going to average out over things. I'm going to take the Poisson specification as is. I'm going to take this, all models are equally likely as is, and just go with the calculations, standard kind of risk calculations. Then I'm going to put these different forms of concerns about model misspecification. The very modest one is the orange one, the green one is the intermediate case, and the blue one, the more severe one. And under the green one, we're seeing on a log scale, the social cost of carbon is increasing here by about 30% in these calculations. Now, this is for a very special model and a special formulation, but it shows you that, at least as a proof of construct, that uncertainty here of the types we're talking about can be very important. Now, what happens after this information gets revealed? So what happens after that gets revealed is that it could be good news. That is, the damage curvature might not, maybe damages aren't all that severe. We cross the threshold. So this shows you the emissions as a function of the damage curvature that gets revealed. I think it's interesting to us is there's this kind of narrow region under which it's the good news scenario, and you decide to emit, I may even increase emissions because we just found out climate change wasn't such a big deal. And there's a very much more substantial region under which caution, and which you continue to be cautious with low emissions and potentially even substantially lower emissions. So it's kind of the asymmetry here is what, and this curvature here is what interests us. Okay. So the summary of our findings here is a solution to this decision problem. It identifies 3 key takeaways. This planner exhibits initial caution until damages are more fully revealed. He doesn't wait until that information comes. It's that there's caution now. Depending on that information, the planner may increase or decrease fossil fuel emissions. It could be good news, it could be bad news as far as damages go. However, there's this pronounced asymmetry in the responses. A small proportion of more bullish increases in emissions and a clustering of more cautious reductions in emissions. So this is one of the kind of first really dynamic treatments of uncertainty in this climate change arena. And we think this kind of puts on the table or illustrates on the table this important trade-off between waiting to get more information versus acting now. So the model that I've done these calculations with is very stripped down. We've largely abstracted from the rule of research and development. Our current research is integrating that in a really central way. And so now there's 2 policy aims here: to not only reduce emissions, but to encourage R&D in terms of the research and development for new green technologies. Now, there's uncertainty in both these components, and our initial stabs at uncertainty here shows a very differential impact on these 2. Perhaps not surprisingly, it's the R&D subsidies where we're finding the biggest impact of these of this uncertainty. Now, the climate model that I showed you was a very, it was a very linear model. Things like that, the climate tipping points themselves were pretty much abstracted from there. The tipping point behavior phenomenon came through in the specification of damages. We're also working with climate scientists about kind of low-dimensional nonlinear models that can induce tipping point-like behavior based on credible climate science. We can't input one of these, enormously large climate models or many of those because they would just be infeasible for us. But there's some low-dimensional ones with nonlinearities that intrigue us that we want to try to that we're in the business of exploring. Finally, along an entirely different investigation, we're looking at the Amazon rainforest and studying the allocation of land. Now land there can be allocated to productive agriculture or to socially valuable carbon absorption. Okay. Now, which we're building spatial dynamic models. We have data on up to 1,000 different locations inside the in the Amazon region, and on which we can measure both agricultural productivity and the ability to absorb carbon. And then we kind of compare actual allocation of activities versus things that might be socially optimal. Now, for us, it's not just that there might be concerns about destroying the Amazon rainforest. It's the allocation of productive activity. Is agricultural production being done in the best places? There's kind of a spatial component to it we find to be very interesting. So with that, let me basically conclude. We think uncertainty matters for tools like the social cost of carbon, for government subsidies of green research and development. Understanding sources of subjective uncertainty used by the private sector and by governments, we think will make economic policy all the more effective. And we think that's, these constructs I talked about early on apply to things more than just climate change, but to other phenomena like pandemics and other things which our historical data sets are limited. Thank you, and I'm happy to answer some questions.
Well, thank you, Lars. That was really interesting. That gives us a lot to think about. Let me take my prerogative of asking a first question. Your policy, your prior robustness term and your model robustness term are multiplicative.
Yeah.
And as a consequence, things that have zero probability in the true model, in the original model, will have a zero probability for all the variations you consider. So, for example, when you think about your 144 models.
Yeah.
There isn't any weighting of them that can make an event not predicted by one of those models occur. So while I think it's very nice to be able to robustify these to some extent, it's not robustifying them in all the dimensions you might be interested in.
Sure. So let me talk about two things there. One is the robustification for the likelihood part. This M part allows us more flexibility than the prior one does, and allows us to explore much bigger spaces of things. But it's still the case there that there's a baseline probability distribution, and that we're only entertaining things that are absolutely continuous with respect to them. So the alternative models can assign probability. The alternative misspecifications could assign probability 0, but so like the M's and N's can actually be 0, but it's true that the reverse cannot happen. They cannot assign positive probabilities to places where the original don't. And so this gets into this whole issue of kind of unknown unknowns and stuff like this. I mean, we're certainly not addressing unknown unknowns in that sense. And I'm not sure I have a great way to do that. In other work, I've been working on trying to relax this absolute continuity restriction in interesting ways, but that's certainly in the calculation I'm talking about today. It's we're using it, but we do want to make the point that the misspecification angle for what we call likelihoods allows us to explore a lot more things than just you would get out of the prior uncertainty. But absolute continuity is playing a central role. I agree.
Other questions?
Yeah, I can't read chat here. You show me.
Dick, what you want to?
Sure. So Lars,
Yeah.
When we talked originally, you talked about how your work differs from Daniel Litterman and Wagner.
Yeah.
And their modeling is obviously a lot less, let's call it sophisticated than yours. But it sounds to me like you might be arriving at similar conclusions. In other words, the greater the degree of uncertainty, and I think some of your results show that, but I'm not certain. Some of them seem to indicate that the greater degree of uncertainty, the more you need to act, or the faster you need to act to counter these uncertain threats. Mm-hmm. Is that a reasonable way to state some of your conclusions?
So I do believe in the calculations we've done that greater uncertainty would certainly, for our calculations, increasing the amount of uncertainty in terms of reducing these penalization parameters would crank up the social cost of carbon. Absolutely. I think the place where, I wouldn't necessarily say they're less sophisticated. They're sophisticated in different ways. They're focusing purely on the risk channel and
right.
on these other channels. They're entertaining in a very serious way technological progress, which contributes to the actual trajectory of their social cost of carbon. Ours is increasing here things as functions of the temperature anomaly, and they get some different time paths of that having to do with speculations about the productive green technologies. And we're just now in the process of trying to integrate stuff like that into our analysis. But okay. Yeah, I would say that the earlier point you made is probably a common theme that we have.
Great, thank you. Rob, do we have other questions from participants?
Let me look in the chat here.
I think so. Not so far. No.
Glenn Beeren raised his hand. Glenn, can you tell us your question? Speak. Let's see. Is it in the chat?
Here he comes.
Can you hear me now?
Yes.
Yes.
That's great. I was a little confused about the concept of the Poisson process.
Yeah.
Or why? Because based on my understanding, wouldn't most of your tipping point be path dependent based upon previous instances of it? And also, isn't normally a negative binomial the classic for climate-based So I'm wondering why you chose something like that, not, or even a compound Poisson on this, just trying to understand the distribution.
Yeah, so the intensity, our Poisson intensity depends explicitly on temperature here. It's not just some ID, Poisson events. There's intensity dependence here. So it depends on what's going on with the temperature anomaly. And you crank up the temperature anomaly to higher numbers, you're going to make that jump all the more likely, and which is part of what we want to get at here. Now, are there richer ways we can imagine proceeding? Absolutely. We did this to illustrate this point about information becoming available in the future. That could be, and so even though that information is going to be available down the road, you still want to be doing stuff now. But I agree that as we want to think about tipping points in a kind of richer terms that we would want to introduce, we want to consider more potentially different specifications of it.
Yeah, because I was also thinking about the anomaly factor, because generally, to my knowledge, and I'm not an expert on this, most of the anomaly is based upon previous 30-year normals. And so when you're looking at that, it's a dynamic number. It's not a set fixed. So if you have a target based on these anomalies, based on your data net set now, in 10 years, it's a completely different factor because it's an auto.
Our temperatures on anomalies all measure relative to a temperature at some pre-industrial notion of global temperature.
Okay.
So that's not changing on us in calculations.
Okay, cool.
But I'm with you that we'd like to be analyzing richer models. Part of what we're struggling with now is figuring out ways to make all this stuff computationally tractable. So.
Thank you very much.
Other questions? Well, let me ask a clarifying question. Are you thinking about this translation from emissions from temperature to damages as being part of the prior or part of the model? And does it matter?
Yeah, good question. Okay, so right now, because the way we've written it as this Poisson jump process, it's part of the model. And so it's a model specification. But one could easily imagine a different specification in which it's we're actually actively learning about damages in different ways, and the damage parameters we're trying to figure out and the like, and then would be and then we place in the prior. It just so happens the way we've set up the calculations now is as jump processes. It's all loaded into the jump distribution, and so then to get at things, and instead of that distribution being parameterized. So if we had introduced a separate parameterization of that whole family of damages, which you might learn about or the like, then that could then one could also try to put prior uncertainty on the table there too.
Yeah. Well, this has been terrific. I mean, and you've got your finger on the problem, because we're having to make these extremely expensive decisions without really enough information, and we can't really wait necessarily. So I think it's very interesting to see how to go forward with this, and I think you've proposed a way to go forward.
Yeah.
But I think we want to see more.
Yeah, so do I. I agree with you on that. I think we've just scratched the surface on things for sure, and in some sense, so absolutely.
So thanks very much, and we'll keep tuning into this.
Okay, great. Yep. Thank you. Thanks for the opportunity.
Thank you, Lars.
Thank you.
Sure.
Well done.